Welcome everyone. Sorry for the technical issue. We're finally here and thank you for joining us for the RecSys 2020 session on evaluating and explaining recommendations. My name is Ludovico Boratto and I will be your chair for this session. Before we get started, I would like to remind you that if you have any question for a particular presentation, you can hop onto the Hoof agenda for that presentation. And if you're on the desktop app, the live video streaming will keep playing on a floating window so that you don't miss anything. We have a tight schedule here, but I encourage you to follow up with the speakers and continue the discussion after the session on Hoof. So without further ado, let's get started. And I will now introduce the first speaker, who is Mesut, and he's presenting our first paper entitled Ensuring Fairness in Group Recommendations by Rank-Sensitive Balancing of Relevance. Mesut, whenever you're ready, you can start.
Yeah, thank you, Ludovico. Yeah. Good morning, everyone. Welcome to the paper presentation for Ensuring Fairness in Group Recommendations by Rank-Sensitive Balancing of Relevance. My name is Mesut and this work has been conducted while I was a research engineer at TU Delft, and this is a joint work with Dr. Derek Bridge from University College Cork and Dr. Tintarev from TU Delft. There are many scenarios where we want to recommend a set of items to a group of people rather than to an individual. And for group recommendations, one objective is to recommend an ordered set of items such that each individual recommendation is relevant for everyone. A common way to do is to select items on which group members may agree on by using so-called aggregation strategies. However, aggregation strategies that select items independently of each other cannot guarantee properties such as fairness that apply to the set of recommendations as a whole. We can illustrate this problem by using a simple example. Now consider a group with 3 people, and also assume that we have 5 candidate items to recommend to this group, and our goal is to recommend a top 3 set of items to the group. Let's say we run a recommender algorithm to predict the relevance score of each candidate item to each group member. And for this example, imagine that an item is relevant to a group member if the predicted relevance score is greater than or equal to 4. Now let's say we use 2 of the aggregation strategies that are called average and least misery strategies to recommend a top 3 to this group. Average strategy computes the mean ratings of the group members as the relevance score of items to the group, whereas least misery strategy takes the minimum rating as the relevance score of the items to the group. So for this example, if we look at the top 3 sets generated by both of the average and least misery strategies, what we observe here is that the circled group member cannot find any relevant item to her in both of the average and least misery strategies, unlike the other group members, and which is unfair to her. This is an example of unfairness that we address in our paper. Even if each individual recommendation is found in a fair way, since they are found independently of each other, the generated top 3 is unfair to the circled group member here in this example. So with average and least misery strategies in our mind, let us ask what a fair top-N group recommendation might look like. First of all, a fair top-N group recommendation must seek to balance the relevance of the items in the set across the group members. So what do we mean by this? Consider the top 3 generated by average strategy from the previous slide, which are the 3 items in the green circle here. If we look at the total relevance scores for each group member, we can see that for the first user, it is 13.5, which is the same for the second user as well. However, if we look at the third user, we can see that it is only 8. And we can say that other group members' total relevance scores far exceed the circled users in this example, which is unfair to her. Now consider another top 3, which differs from the previous one by only the last item. What we can observe here is that for this top 3, compared with the previous one, the relevance of the items in the set is more balanced compared with the previous one because of the third user here. And in our work, since the order of the items in the set is important as well, we say that the top-down group recommendation will be even fairer to a group if it seeks to balance the relevance of the items across the group members for each prefix of the top-down. So what do we mean by this is that, so consider two different permutations of the circled three items, for which the first item is the same. What differs is the position of second and third items. So if we look at the total relevance scores of items at each prefix, since the first item is the same, we will move to the second position. What we observe that if we take the first items and second item together, their relevance score together, we can see that for the first permutation, the relevance is more balanced across group members compared with the second permutation's total relevance scores. So this is the rank-sensitive balancing of relevance that we speak about in our paper. And of course, if we look at the third position, since both permutations have the same set of items, the total relevances will be the same for both sets here in this example. So this leads to our formal definition of fairness, which is a top-down group recommendation is fair to a group if the relevance of the items is balanced across the group members for each prefix of the top-down. In other words, the first item should, as far as possible, balance all group members' interests. The first two items taken together must do the same, and the first three items, and so on up to n. And based on this definition of fairness, in our paper, we provide a greedy algorithm that we call group fairness-aware recommendations for finding a top-n order set of group recommendations that satisfy our definition. Current fairness-aware group recommendations methods do not define fairness in a rank-sensitive way, the way that we do, although some achieve a degree of rank sensitivity through the greedy algorithms. So if we move to the experiment, in our experiments, we used two datasets, one from each of the music and movie domains, and we created a synthetic group of varying sizes. And we created three different types of groups based on the similarity between group members' interests that we call random groups, similar groups, and divergent group. And we used 10 evaluation metrics adapted from literature to compare the performance of our approach to other approaches. This leads us to 210 cases per data set. And finally, we compared the performance of GFAR to 5 approaches from the literature, which are average and fairness aggregation strategies, and 3 of the recent fairness-aware group recommendation algorithms that are called XPO, Greedy LM, and SP Greedy. So if we look at the summary of the experimental results, what we observe is out of 420 cases, for 43% of the cases, our approach GFAR is the best performing approach. And the difference between GFAR and second best performing approach is statistically significant. And again, for other 29% of the cases, GFAR is the best performing approach. However, the difference between GFAR and the second best performing approach is not statistically significant. And for only 18% of the cases, any of the other approaches is the best performing approach, and the difference between the best performing approach and GFAR is statistically significant. And finally, for the remaining 10% of the cases, again, any of the other approaches is the best performing approach. However, the difference between the best performing approach and GFAR is not statistically significant. In the experimental result, what we also observed that it is more difficult to find fair top-down recommendations for groups in which the members' interests diverge. So in other words, it's slightly easier to find fair top-down recommendations for similar groups compared with divergent groups. And it becomes more difficult to find fair recommendations as the group size grows. So for example, it is slightly easier for finding a fair top-down recommendation for a group of size 2 compared with a group of size 8. To conclude, in our paper, we present a novel definition of fairness for group recommendations that we call GFAR. And GFAR is rank sensitive in the sense that it defines top-down as fair if the relevance of the items to the group members is balanced across the group members for each prefix of the top-down. And we find out that experimental results on 2 datasets show the effectiveness of GFAR. For the future work, we are planning to apply GFAR to NIP domains. And most importantly, we are planning to conduct user trials to test GFAR's effectiveness on reals, since gaps exist between serving recommendations to real-world groups and synthetic groups. Thus, the assumptions that we made based on offline experiments might not be valid in practice. And finally, we are planning to investigate variants of GFAR, such as allowing user-specific weights. And thanks for your attention. This is the end of my talk. And some advertisement about myself. I'm currently in the job market. If you want to reach out, please check my Whova profile. And if you have any questions, I will be glad to answer them. Thank you.
Okay, thank you, Mesut. So we do have some time for the questions, so I encourage you, if you haven't done so yet, to post your questions in the Q&A section of Whova. I will start with one.
Yeah.
So basically, your approach kind of ensures fairness without any expense in terms of accuracy, which is a great property, which is usually not the case in most papers with fairness. It's usually a trade-off between the two. Mm-hmm. Do you have any insight? Have you made any consideration in this sense? Is it because your accuracy metrics are also rank-based, or, I mean...
yeah. I mean, so that can be one case, but to be sure, that's why we used several alternative metrics, right? We use, for example, recall, which is not rank-sensitive metrics, and we used NDCG and the discounted first hit, which is again rank-sensitive. So what we observed here, that for all metrics, our approach for the average of the metrics, which is basically not a fairness metric, right? You are just taking the average NDCG of each group member, was performing the best here. And also we were performing in terms of the fairness metrics that we call mean max ratio and minimum, which is, like you said, normally maybe you expect a trade-off. I think here there can be several reasons. It can be the data sets that you are using. It can be the baseline algorithm that you are using to generate, individual recommendations. But I guess the most important point is the smoothing factor of our approach. Since it is a greedy approach and it is based intent-aware diversification, I mean, our motivation was coming from intent-aware diversity, like it is like probabilistic framework. That is why it is not strict as the previous group fairness approaches that say, for example, a set is fair if there is at least 2 relevant items to a group member. We are not saying this. It is based on the probability of the relevance of the items.
Okay. We do have time for another question from the audience. And the first question is, have you looked into election method like Condorcet?
No, actually, I didn't hear about that. And this is my bad, I guess. Maybe we can have further discussion about that.
Yeah, offline. And there was another question that says, how can we efficiently find the optimal permutation in terms of GFAR?
So what, I mean, the optimal permutation, what do we mean by that? So is it like, it is not talking about hyperparameters, I guess. I mean, is it like optimal permutation of the final set of recommendations? I do not get this question, I guess.
Okay, so maybe, yeah, it's in Hoover, so maybe you can discuss this.
Yeah. I can ask to the question.
Thank you, Mesut. Thanks again.
Thank you.
And, so we can move to our second presentation, and our next speaker is Huang, and she's presenting a paper entitled "Keeping Dataset Biases Out of the Simulation." Keeping dataset biases out of the simulation, a debiased simulator for reinforcement learning based recommender systems. Jim, whenever you're ready.
Yeah, thanks. So welcome to our presentation for our first paper, Keeping Dataset Biases out of the Simulation, a debiased simulator for reinforcement learning-based recommendation system. So my name is Huang. This is a joint work together with Harrie Oosterhuis, Maarten, and Herke van Hoof. So we just jump to our main contributions. First, we find where the existing simulators allow offline IL-based recommendation system learning, but they ignore the biases present in logged data. So we introduce a way of debiasing simulators to mitigate the effect of the bias. And we also find the simulators haven't been evaluated based on the performance of their produced policy, despite a well-performed policy is the ultimate goal. So we introduce a novel evaluation method and evaluate the effect of bias on the final policy performance of a simulator. Where the first two contributions can be applied to any reinforcement learning-based recommendation simulator, we combine them in a newly proposed simulator for offline learning and evaluation. We called it SOFAR for short. Before I present our work, I would like to start with a brief introduction of two backgrounds. The first is I-alpha-REC. So the left figure displays the typical flow of I-alpha-REC. A state is historic interactions of a user who is about to receive a recommendation. And an action is an item being recommended by the policy of the recommendation system. And the reward is implicit or explicit user feedback. The goal of R-alpha-REC is to maximize the cumulative rewards over multiple sequential recommendations. But R-alpha-REC approach brings risks when applied online. An alternative to online experimentation is the simulation-based experiments. So you can see in the red figure, the user feedback on items is simulated according to the logged data. The second background is interaction bias in logged data. We take a positivity bias as an example. It occurs because users rate the items they like more often, and this results in positive feedback of the training set being overrepresented. As a result of bias, the logged data is not uniform randomly observed, and the missing slot in the rating matrix are missing not at random. Formally, the MNAR is often modeled by separating the probability of observation and the probability of a rating. So if every rating is equally like to be observed, so that means there is no bias. All the users and the items are equally represented. When the positivity bias is present, the items that receive higher ratings are more likely to be given a rating. So without the correction, the bias may affect the rating prediction and further influence the I-alpha-REC simulators and the produced policy. We use a very simple example to estimate the average rating of an item. And the naive estimation is simply the average of the observed ratings. But in expectation, you can see the naive estimate is affected by the observation probability. If there is no bias, so the estimate is correct in expectation. But if the positivity bias is present, the estimate is expected to overestimate the true average ratings. So that's why we want to debiase a simulator. We focus on our I-alpha-REC simulators with a predicted user item rating matrix to model user preference and a user choice model to simulate user feedback. As we discussed in the background, the logged data suffers from the interaction bias, and the predicted user item rating matrix is affected and biased. Then the simulator is biased, and finally the produced policy is also biased. If we unfold the whole flow, we can go to the second figure. So this poses a question because the simulated user behavior shouldn't be affected by the way a dataset was logged. So that's we propose the intermediate bias mitigation step IBMIs between the logged data and the learned prediction model. We hope it can minimize the effect of the bias to reach the subsequent step, including the final produced policy. Then we have so the IBMS can apply any debasing method. Here we use the inverse propensity score. The key idea of the IPS is inversely weighting the logit ratings in log loss function, and it can be proved that the expectation of the IPS loss based on the logit data provide an unbiased estimate of the full information loss. Then we have another question, how to evaluate if the proposed IBMS mitigate the bias from affecting the produced policy or not. So the existing work has evaluated the IR4REC simulators by comparing their simulated feedback with logit user feedback, showing the left figure. The downside is they don't consider the performance of the policy learned with that simulator, but we consider this aspect. So we propose an offline evaluation method based on the performance of the final produced policy. And our evaluation methods only requires a sparse set of missing complete at random ratings, which can be gathered on randomly selected items. And the evaluation methods consist of the following 4 steps. First, train a policy using a simulator with IBMS on MNAR rating dataset, so we can have it results in a debiased policy. Second, train a policy using a simulator without IBMS, so it results in the biased policy. Third, create a simulator based on MCAR ratings, because the MCAR rating is unbiased, so this simulator is also an unbiased simulator. Finally, we deploy debiased and biased policy in this unbiased simulator. By comparing the cumulative rewards of debiased and biased policy trained with and without the IBMS in a simulator, we can see if the IBMS truly remove the effect of bias or not. Recall the flow of IR4REC with a simulator shown in the figure. We show our newly proposed simulator so far. It consisting of 2 components. The first is a debiased user atom rating matrix produced using the IBMS with applying matrix factorization with IPS. And the second is a user choice model to simulate user feedback on the atoms being recommended from recommendation system and provide the updated state and the immediate reward back to the recommendation system. Our experiments aims to answer 2 main research questions. So the first, does interaction bias in logit data affect the simulator? Second, can IBMS mitigate the bias effectively? And the left plot shows the learning curve of 2 policies. One is learned with a biased simulator, the naive sim, and the other is learned with a debiased simulator, our so far. So we can observe that the cumulative number of clicks for policy learned with naive one is consistently higher than the so far. So it's a little weird because our method is so far, but it's noteworthy that the learning curve are based on the numbers of clicks received during training, and they are unreliable estimate of actual performance because of the bias. And the right plot shows the evaluation results of 2 policies. And the policy resulting from using so far outperforms the one using the naive simulator. So this outperforming of the policy learned with so far can answer the second research question positively. And the reversal of the learning curve and the evaluation methods can answer the first research question. Yes, the interaction bias in logit data does affect a simulator. So in this paper, we analyze the effect of bias on IR4REC simulators and the produced policy. The proposed intermediate bias mitigation step can mitigate the effect of bias. And we also propose a novel way of evaluating the effect of bias based on the performance of the final produced policy. And we also proposed so far the first simulator for I-alpha-rec with correcting for bias. In the future work, we will consider the effect of interaction bias on simulators for multi-atom recommendation scenario. Because this work, we only consider the single atom recommendation, and we will care more about the widely relevant recommendation task, such as the ranking task with using implicit feedback. That's it. So thanks for listening.
Thank you, Jean, for your presentation. We do have time for some questions. And the first one is, how does the recommendation like for results from biased data sets? Is there any example? Are they very different to the results that you obtain from an unbiased simulator?
So there is some existing work they talk about the and so this question is asks for when the dataset is biased, how is the recommendation? And actually, in our case, we use a dataset who has biased the training set and the unbiased test set. So based on the unbiased test set, we can say if our method can mitigate the bias or not. But if we only have the biased data set, including the biased training set and the biased test set, maybe it's hard to say if then the proposed mitigation step can make it or not. So I'm not sure if anything we can do with biased data sets.
Okay, thank you. And then there's a second question that asks, have you tried changing the slate length in the research to study bias?
Thanks for the question. We don't consider this, but talking about the changing the slate lines. So, because in this work, we only consider the single atom recommendation. And I'm not sure if this related to our research or not. Sorry for that.
Okay, thank you. Then, okay, there are no more questions. So thank you, Jean. And we move to our next speaker, who is Pablo Castells, who will present a paper entitled On-Target Item Sampling in Offline Recommender System Evaluation. Pablo, whenever you're ready, you can start.
Okay, thank you, Ludovico. And hello, everyone. I'm Pablo Castells from the Autónoma University of Madrid, and this is joint work with Rocío Cañamares on better understanding the effects of picking different sets of target items in offline evaluation. This is a particular aspect in designing experiments that has not been paid much attention, and we want to better understand the effects of this setting, what the options are, whether they can affect the result of an experiment, and if possible, some hint as to how to best handle this. So let me start by explaining what we mean by target items and giving some context. Imagine you have two recommender systems, A and B, and you need to find out which one is better. And for whatever reason, you cannot afford an online A/B test, so you run one or more offline experiments. In an offline experiment, you collect some offline data with observed user activity. The data involves a set of items that your evaluated system should recommend. You typically split the data into training and test subsets, which you can do in many different ways. Then you pass your training data as input to your evaluated systems. And then for every user, you ask your systems to rank the items. You compute some metrics on the rankings using test data. You compare and you come to some conclusion as to which system seems better. Your goal in offline evaluation is that it represents your real scenario as well as possible. And you may be aware that this is not necessarily easy, and it's actually an open problem. But you also want your experiment to be consistent and comparable to other experiments so that we can build on the work of each other as a community. So you need to be careful with many details in how you design your experiment. With that in mind, there is a particular design detail that is often implicit in offline evaluation, and it's the selection of the target items. So target items are the items that you ask your evaluated systems to rank, and this is not necessarily all items. So why would you take a subset instead of just all items? Well, to begin with, in most cases, you don't want your evaluated systems to recommend items that have training data for the target user, so you don't put those on the rankings. So in practice, you usually take a subset of target items, even if you didn't intend to. And it has become increasingly common, in fact, to take smaller sets to reduce the cost of experiments, or maybe for other reasons. So the question is, does it matter? Can you still rely on the results if you're ranking fewer items? Or maybe, who knows, maybe your results can be more reliable by taking fewer target items. So first of all, what are the options when picking target items? So first, we may consider that any sensible option should include at least items with a test rating and no items with a training rating. So in terms of the number of target items, the option then would be how many unrated items to include. And we can go from all unrated items, which is the typical option in the literature, to no unrated items. And we can take any number of unrated items in between. So now the important question is, can this setting affect the result of evaluation? It certainly does. It's very easy to see with just a simple toy example like this one. So let's say we have these two rankings, and with all unrated targets, A is better than B because A returns this green item representing a relevant item in the top two, and B returns just two white unrated items. If we now remove unrated items from the rankings, you can easily see that now B is better than A because now B returns two relevant items in the top two. Now the question is this just an artificial example, or would we observe things like this in experiments with real data? Well, let's try. So let's run a typical offline experiment with movie lens 1 million, 8 systems, a random split. We measure precision at 10, and this is what we get. We evaluate with all unrated items in the target set on the left, and then no unrated items on the right. It doesn't really matter which specific algorithms we evaluate here. The thing is, we may see many interesting observations, but let me focus on the most important ones to make my point. And for this purpose, let's check the order of algorithms from best to worst in precision at 10 here. And we can see that the order is not the same if we take all unrated items or no unrated target items. We can see this better with lines. So each pair of crossing lines represents disagreement in the comparison between a pair of systems. And you can see a considerable number of disagreements, which is also reflected by a very low Kendall correlation. So this is really something to worry about because we would come to totally different conclusions with different target sets. Even more important, the disagreement is not by chance, but there is a systematic bias. Let me explain this. For instance, recommending popular items gets better results when evaluated with many unrated target items. The same happens when taking into account unrated items in the objective function of your algorithm when training your model. On the other hand, taking few target items favors models that ignore unrated items when training, and the recommendation of items with a high average rating as a particular case. And the parameter settings that work better with each target size are completely different. All this is worrying because your experiment can give contradictory advice depending on the number of unrated items you take. And the tricky question is, which result should we trust? Like maybe, should we use all unrated items every time? And how would we know? So here's an idea. Since we want our experiment to match online evaluation, let's compare to unbiased evaluation. Even if we don't have a running system to run an A/B test, we can use a data set like Yahoo R3 that has both random and non-random ratings so that we can do both biased and unbiased evaluation and compare. And this is the result. In the line graph of system rankings, we now put unbiased evaluation in the middle, so we can check how much the big and small target sets agree with unbiased evaluation. We see a good number of crossing lines in both settings, perhaps a bit more when we use no unrated items on the right, but taking all unrated items here on the left is not that good either. So, given that the extremes do not seem to match unbiased evaluation that well, how about some number of unrated items in between? So let's check that. So we now check the Kendall correlation over the whole range of unrated number of unrated target items, from all unrated items on the left to no unrated on the right. You see that indeed there seems to be some better points in correlation with unbiased evaluation in between the extremes. In particular, it seems like about 100 unrated items might be a reasonable choice. So this could be a good criterion to find what a suitable number of unrated items can be. The problem is, how about any usual data set that doesn't have random ratings? So we cannot do unbiased evaluation or measure the correlation. Like, how do we know what's a good target size in movie lens? Well, here's an idea. Let's check the discriminative power of the experiment. And this means the capability of evaluation to distinguish between two systems with some certainty. So as a way to analyze discriminative power, we check the number of ties in the experiment. The number of ties is the number of users with the same value for precision at 10 for some pair of systems. We show this with the blue curve here, where lower is better because it means fewer ties. We see some correspondence between the curves. The blue curve, the number of ties, is almost a mirror of unbiased correlation. Both suggest a similar ideal number of unrated targets. So minimizing ties could be a good criterion to settle for a target size also in movie lens, perhaps. Tie analysis would confirm that many or very few unrated items may neither be the best option in general because they both produce many ties. And why is that? On the one side, with very few target items, the number of possible rankings becomes very small. So systems have a hard time in producing a different ranking from each other. On the other extreme, with many unrated items, relevant items can get kind of buried in the pile, and it becomes increasingly difficult for the evaluated systems to rank them in the top 10. So more and more users and systems get zero precision, which means more and more ties. So we have analyzed discriminative power in terms of ties, but the usual tool for this are the traditional statistical significance tests. So we check those two. For this purpose, we sum the p-value of a t-test for all system pairs in each experiment. And we show this in the graph with the black curve. We see it is less clear than the blue curve. It would seem a bit noisy, a bit shaky, especially here in movie lens. The correspondence with unbiased evaluation is not as clean. And in fact, it's actually known that statistical tests don't handle ties very clearly, meaning that you may have many ties and you don't necessarily get high p-values. So the number of ties seems a clearer reference for our purpose than traditional statistical tests. Finally, small target sets have an additional weakness, and it's that they can cause incomplete rankings. Some algorithms may not be able to rank as many items as the metric cutoff requires, given a too small choice of target items. This can mess up evaluation seriously if we don't realize it's happening, and we don't handle incomplete rankings in a consistent way. And this is an additional cause of disagreements when using different numbers of target items. So to conclude, target items do indeed make a big difference in the outcome of comparative evaluation. The difference is biased differently for different algorithms, and either extreme in target size seems ideal. The weakness of taking few target items is that it gets difficult to produce different rankings, and on the other hand, you may get incomplete rankings. The weakness of taking many target items is that they may cause a higher exposure to non-random biases, and it's also more difficult to produce metric values greater than 0. So in both cases, we have a loss in discriminative power. The sweet spot in target size that we have found may reflect a balance between these weaknesses. Finally, in our analysis, we find that the number of ties can be a useful discriminative power measure, even beyond our current purpose. It is smoother, more stable than p-values, it's easy to understand. In our case, it seems to match correlation with unbiased evaluation, so it can help choose an appropriate target size. We don't think all questions are answered by your research, and more research is needed. In particular, sampling target items, in fact, implies adding a pre-filter to recommendation algorithms, and this perspective could be further analyzed. Another question is, do our experiments with Yahoo actually match online evaluation? This could be answered with actual online evaluation and maybe further offline data sets with missing at random data. Finally, let me mention 2 papers that were just published at KDD last month. They address the exact same problems as we did, but focus on different angles. Our findings are complementary and confirm each other on several points. So if you are interested in this topic, I highly recommend reading them. And with this, I thank you for your attention, and I'll be happy to take your questions.
Thank you, Pablo. We do have some minutes for questions, so I encourage you to use the Q&A section of Hoof if you haven't still posted your question. The first question that comes from the audience basically is asking you to elaborate a bit more on the paper that you just mentioned, the KDD 2020 paper entitled On Sample Metrics for Item Recommendation. How do the 2 works relate?
Yeah, there are, interesting differences in perspective. So that paper doesn't question whether taking all unrated items is the best option or not. It kind of takes it as a given. So assuming that that's the best option, they find that there may be disagreements if you take fewer target items. So we reached the same conclusion. Only in our paper we also question, but is the biggest target set actually giving you more reliable results or not? And we find that it's not necessarily clear. So that's one difference. Another is that it's a technical detail, but it can make a difference. In their case, the type of data split they do is not like us, like random split, but leave one out. So it means that you only have one relevant item in each ranking. And then finally they go beyond also what we do, which is they propose an approach to compensate for the disagreements. So when you have few target items, they do a compensation for that, and so that the results agree better than they would normally. So it's a very nice paper. It includes a theoretical, an analytical development as well. So I see it as kind of really complementary to our work.
Okay, thank you.
I think we don't reach contradictory findings.
This is good. So basically, we started a bit late, so there are no questions, and I encourage you to go to the Q&A section to react with those questions and answer them. So thank you again for this presentation.
Thank you. I'll be happy to do that. Thanks.
And we can move to the next paper, which is entitled Recommendations as Graph Explorations, and it will be presented by Maria Elena Kyriakidi. So Maria Elena, whenever you're ready, you can start.
Let's see. Okay, one moment. Okay. You can hear me, right? Okay. So, hi, I'm Maria Elena Kyriakidi. I currently work at Google Research in London, but the work that I will be presenting you here today was done with my colleagues at the University of Athens, and is called Recommendations as Graph Explorations. But first, let's start with a bit of motivation. So recommenders are becoming the core part in many industrial systems today. And as a result, their usage increases and they are becoming more and more diverse. So we noticed the recommendation diversity and we classified it in 3 main aspects. The first one is diversity in the information space. which actually means that we have data that it's heterogeneous, interconnected, that regularly grow in size. Number 2 is diversity in the recommendation goal. This means that what is being recommended and to whom may change over time, and it depends on the current application needs. And lastly, we have the recommendation mechanisms that are used to generate the recommendations, and that can vary from traditional collaborative filtering techniques to deep learning and many, many more. Now, all of this has led to an enormous amount of recommenders that seem different and are in fact tailored solutions for very specific tasks within a specific domain and in a specific information space. And I put specific 3 times on purpose there. So all of this actually suggests that there is a lack of methodology towards recommendation, that it can lead to complexity, and that complexity can be quite problematic. So why is that? So first of all, we have solutions that are very, very good. But the thing is that they are not easily reused. They cannot be generalized or adapted to different or novel problem settings. There is much replicated effort going on, and even the optimizations can be handcrafted and case-based. Lastly, the experimental comparison and evaluation can also become quite troublesome. Now, what we did is we tried to look at recommendations in a slightly different way. And we argued that most recommendation approaches can be abstracted as a graph exploration problem. And we formulate a methodology around this very argument. So we proposed RecGraph, which is a graph theoretic approach to recommendations, and it consists of a data model and a computational model. Now, this model is uniform, and it has a small set of abstractions. And these abstractions are important because they help us capture different recommendation elements. They help us explore connections in a heterogeneous data space. They facilitate the design and evaluation of algorithms, and they enable scalability whenever this is possible. This approach, our approach, was inspired greatly by the success of data management systems. And we think that this is a very good first step towards recommendation management systems as well. But now let's look a bit at the details of the model. So first, you can see this is an example of the RecGraph data model. So as you can see, the data model is a graph. And the graph has entities that are relevant to the recommendation domain. And they include things that can be recommended or can receive recommendations. These are the nodes on the graph. The edges can be of multiple types, and they include relationships that can be domain-specific knowledge. They can denote a state, an attitude, a preference, and many more. Also, notice that in the graph, on the figure, there are some blue node and edges versus some gray ones. So the blue ones are information that are relevant to the schema, while the gray ones, they are instantiated information. So we have both instance and schema information in the same model, and we use it. And now let's take a small example and suppose that you want to ask a recommendation question using our model. So let's suppose that you want to ask, does user Johnny likes or wants to go to a restaurant named Kenko? Now, when you ask a question, a recommendation one with our model, this transforms into a reachability question between 2 nodes in a graph. So you abstract from the question at hand, and you can map it on the graph. So what you are asking is essentially, is there a path between these 2 nodes? Keep this in mind, because these abstractions is what I will present next. And this is the more formal definition, where we can see that we define recommendation as a path problem. I don't want you to read the slide. I just want to point out these 3 things. These are very important because these are the 3 operators that are our computational model. And we really need those things to move on the graph that we formally defined. And to elaborate a bit more on that, here are the 3 operators again. So these operators are edge operators, so they are responsible for deducting an edge. The first one is used for traversing consecutive edges and is called con. And the other two, they are quite similar. They are used to combine multiple edges between the same set of nodes. There is a difference between them. So AG, which is the first one, it uses edges that have the same labels, but Fuse, on the other hand, it uses edges that have distinct labels. Now also notice, and I will put it up here, that these operators can exhibit several mathematical properties. I cannot list them all here, but they are listed in the paper if you want to see. And this is a very important part of the problem because we will use them later for optimization purposes. Now, if you want to write a recommendation algorithm using our framework, you will have to use only these three operators, and you will do it with the query language that we also introduce here. So this is how you write a program using our framework. And after you write the algorithm in that way, then the algorithm is communicated to a graph engine that runs it. So RecGraph is written in Java, and we run it on top of Neo4j, which is a very popular graph database engine. It could be any engine really, but we chose Neo4j because it is fairly popular and everyone knows it. And now that I mentioned this, let's talk a bit about why would you want to use such a system. So there are the benefits. So actually, we think of a recommendation process as something that consists mainly of user and system interactions. So we tried to improve on both fronts. And we denoted expressivity and usability as the two things that benefit the user side, while processing speed benefits the system side. Now, expressivity can be achieved from the abstractions, both in the data model and the computational model. So the abstractions in the data model can help capture the heterogeneous recommendation space and abstract from the application specifics, while in the computational model, you can use it to capture different algorithms and recommendation goals with the same uniform logic. We also show how to model this on several algorithmic families. They are in the paper. They are similarity-based, matrix factorization-based, and we even hint on neural network approaches. Now, usability is a bit easier to see because we use the declarative query language that I previously mentioned. This helps designer focus on the recommendation logic rather than on the implementation details. And the code needed is shorter, typically, and it's easier to understand. It's something that usually happens with logic-based languages. We are not just saying that for ourselves. We also conducted a user study at the university to support this argument. Lastly, let's move on to the processing speed. So RecGraph is implemented on top of a graph engine, and graph engines are known and are designed for interlinked data scalability. So the good thing about this is that they also come together with an optimizer. And if you remember the mathematical properties that the operators can exhibit that I mentioned earlier, the combination of the optimizer with the properties can help us improve speed. I can demonstrate how in the next slide. So now let's suppose that you have a user, and the user writes a program, a recommendation algorithm using our language. Then this program is translated into the engine in this execution plan that you see on the left, the initial plan. So this is what the user wrote. Now, this is not a bad plan. It can be executed. But the thing is that this is rather slow. So this is where the optimizer comes in. The optimizer can use the operator properties, some statistics on the graph, take the initial plan of the user and transform it into a different plan, which is optimized and can run very faster, which is the figure depicted on the right. Now, we checked this speed because we also performed some experiments. The experiments were done on Yelp dataset. We chose Yelp because it is a very semantically rich dataset, and we were trying to capture different types of recommendations. We chose some typical examples of content-based and collaborative filtering techniques, and also social recommendation algorithm and package recommendations. As you can see here, there are like three main clusters in its figure. So the first two, RecGraph 1 and RecGraph 2, they are programs that were used using our framework, while the third one uses Cypher, which is the native language that Neo4j uses. In all of these cases, even in the ones that you can't really see, but I magnified here, there are the middle column wins, which is the optimized plan produced by the optimizer. And with this, I will end here my talk, and I would just like say again that thank you. This is our approach on a generic graph-based framework for recommendation, and I hope you liked it. And thank you for watching.
Thank you, Maria Elena, for your presentation. And we do have time for some questions. So if you have some, please use the Q&A section of Huba. The first question coming from the audience is, did you implement matrix factorization and KNN-based methods? Did you compare the runtime performance against existing implementations?
So we basically wanted first to, the real thing that we first wanted to see is if we use methods that rely heavily on graph engines, how we will do. So the comparison was done initially with Cypher because we wanted to see how the optimizer will behave if it uses the native language of such a system versus our framework on top of it. So at the next step, we will also compare with the main, other libraries that exist out there. But, it's a different direction of the project. So we didn't do it on this one, but it's on the plan.
Okay. Thank you. Second question, what's the advantage of your graph recommendation method compared to existing graph method like random walk?
So the thing is that we don't really propose an algorithm here. What we propose is a framework that can express different algorithms, all the new ones. So we're kind of like trying to develop a uniform logic to write recommendations, because when you miss this, when something is not uniform, you kind of like miss out on optimization opportunities. This is why we try to limit the number of available recommendation approaches and put it in something like dimensionality reduction, and put it with only express it with 3 operators. But it's not about a specific algorithm. You can express anyone in the system.
Time for one last question. How do you assign the weights to the edges?
So again, this is has to do with what kind of algorithm you need to, you want to express. We provide a way to do it. There are some thoughts, which is like my favorite thing actually to do, on how the system can automate this but on its own. But currently, we offer the framework and the logic and the optimization techniques, but you have to define what type of algorithm and how to set the edges to increase the quality in the recommendation result. So this is not speed. This is about the, the recommendation result quality, which is quite different. It depends on the algorithm that you use and not on the infrastructure.
Okay. So let's thank again our speaker, and we can move to our next paper, which will be presented by Darius Afkar, and it is entitled Making Neural Networks Interpretable with Attribution, Application to Implicit Signals Prediction. Darius, whenever you're ready, you can start.
Yes, hi everyone. Okay, so I'm presenting a work on neural network interpretation done at Deezer Research with Romain and Chen. So to add a bit of more, to have a bit of context, interpretation is a vast field, and for recommender system, there has been a substantial work on finding ways to explain and justify recommended items to users, since it has been shown to improve users' forgiveness for bad recommendations and their overall trust in a recommender system. And a little more understated branch of interpretation is the analysis of how a model actually relates its input to output and how it makes its recommendation, which has many applications ranging from debugging a model to ensuring recommendation fairness. But more than this, it tells a lot about the data we are handling, and it can be used, for instance, to interpret implicit signals. So quite typically at a music streaming company like Deezer, we try to model users' intent and tastes, which are highly subjective, especially for music, and only based on weak indicators that only implicitly translate their tastes. So for instance, if we look at a user listening session, it is straightforward to create models that will predict and anticipate the track you are going to listen versus the track you will not listen to, that you will skip. But it is not obvious to additionally interpret if this is because you didn't like the music, hence we may adjust your recommendation taste, or just shuffling through the catalog, and hence we are adjusting the type of track you're recommending to just recommend fresh content or something completely different. And one way to solve this is through the attribution task, which is more general than just interpreting skips for Deezer, and means that we want to know for prediction what input features were the most salient to make this prediction. So formally, starting from a supervised prediction task, with an input random variable x that we try to map to a target variable y through a parameterized family of distribution, f theta. The attribution task consists in adding a random set of indices, S, and optimizing it with two contradicting objectives. So predicting Y from the X now restricted to the set of indices S, and that while having S as small as possible. So those two objectives are often referred to as completeness and interpretability. However, the problem with attribution is that for n-dimensional input, we have 2 to the power n candidates for the restriction S, meaning that if we had infinite computational power, we would train many models, each on a candidate restriction, and we would solve the attribution by selecting the right model with low error value and small domain dimensions. But this makes, as you can guess, attribution typically NP hard, and there are many other issues at stake, as dealing with overlapping subsets or ensuring the unicity of the solution, and of course, not degrading the model prediction performances. So that is why many methods see attribution as a secondary task. So they either solve a proxy task, think of Lime or smoothgrad of saliency, or resort to variational approximation to avoid this prohibitive computational cost. And another branch of attribution method, however, try to incorporate this task during training by modifying the model structure. So, for instance, you can formulate your model as a sum of univariate contributions, which allows to check each individual feature impact on the prediction, or then you can add a pairwise interaction trained on residual points to further inspect the feature interactions. And our method falls into this last category of interpretability methods because we will model our predictor as a general weighted sum of several multivariate submodels, each restricted on a specific subset of interest. So our contribution will be the following. We will propose a novel approach for attribution and show that we can make many deep neural network interpretable. We derive a fast algorithm to train them and show that they are effective for both prediction and interpretation on real and synthetic datasets. So now to the method. Well, prior to attribution, there is a very important hypothesis we make, is that for real data applications, the exponential number of candidates we can expect for a selection of indices can often be reduced. And for that, we leverage two ideas. The first one is group sparsity, meaning that we can often partition our input into a coherent group of features, and we can only consider co-selection or co-deselection of those groups, and hence first reducing the space of candidate to only 2 to the power the number of groups we consider. And the second idea is structured sparsity, meaning that we often have an idea of the sparsity pattern we can obtain, and we can further prune the space to only, let's say, H candidate for sparsity. And we suppose that H is reasonable. So now that we have this hypothesis, we can train actually H submodels, restricted submodel, each restricted on a candidate subset. But how do we combine them, those H model, into one final predictors? As mentioned, we'll use a weighted average. So we will weight each submodel by some selection function alpha. But how do we choose the alphas? So let's take a simple case. Imagine that we consider a problem with bidimensional input with all the three possible restrictions. So we will have two univariate functions and one bivariate function. As we want to use the minimal number of input features, we will either make a prediction using F1 that only uses X1, F2 that only uses X2, or if we couldn't predict what we want to predict, and in last resort, we'll use F3 that uses both input features X1 and X2. And to translate this else condition, we'll use boosting. So in particular, the selection value of F3 should be high if and only if the selection value of F1 and F2 is low. And in the general case, which can this can be written as this. So alpha S will be a self-selection function, GS, times the deselection of all of its children. So children is a sense of included subsets. So in details, to implement these self-selection functions in the binary settings, for instance, and given a subset S, we propose to use a single neural network with codomain -1, 1 that will be used for both the prediction and the selection. It's absolute value for confidence. And other functions may be used to control the error and the confidence, but the overall idea, for instance, for the binary setting, that the closer the prediction to either -1 or 1, the more confident the model about its own prediction. So I don't have much time to explain, but this specific formulation allows us to emulate several all of our H submodel into actually a single overarching neural network. And the trick for that is to use to mask the weight of the model, which is really easy to implement and allows to reformulate with a bit more work, many complex architectures, for instance, a recurrent neural network or transformer into interpretable one. And of course, you can find more detail on the paper and on the GitHub. And lastly, the last step is to train everything. So naively, we could train our submodel sequentially as previous methods in a boosted manner. So first the univariate function, and then the bivariate on residual points, and so on and so on. But thanks to the way we've defined our alpha functions, we can do that jointly using an EM scheme. So during the E step, we will estimate our selection, what's the model we select, and during the M step, we will maximize the expected likelihood. But because we are dealing with neural network, we cannot do an exact maximization, so we just perform a gradient step. So it's what we call generalized EM. So we did evaluate our model on several tasks on the two objectives of completeness, so prediction, do we degrade the performances, and interpretability, or the attribution relevance. So first, we just report the result for the sequential skip prediction for both a Deezer dataset and a Spotify dataset. So the key takeaway is that the performances of our interpretable models are reasonably close to their non-interpretable counterparts. But that while selecting and restricting themselves to a minimal number of input features. Interpretation is way more difficult to evaluate. So we can check, you can see that on the paper, that everything works properly on synthetic tasks for which a ground truth attribution can be computed. But on real data, we can only check expected behavior of a solution or axioms. So in this cherry-picked example of skip prediction task, if you remember the introduction example, we wondered if we were able to distinguish between a musical skip from an interaction skip. Well, this is what our model allowed us to get. Well, for instance, in this session, this is mostly a rock music-based session, there is a sudden Malaysian pop music in the middle of it, and our model captures it and will highlight it as a musical skip because it's incoherent with the rest of the session. So that's it. Thanks for your attention. And again, please read the paper for more details and check out our GitHub repository.
Okay, thank you, Darius, for the presentation. We do have some time for questions, so I encourage you to use the Q&A section of Google if you haven't still asked your question for this paper. And the first question from the audience is, could you give examples of attributions?
Well, the skip prediction one is an example. So let's say that you have tracks. So track data, usually you have many multifactorial data. You have the audio signals, you have collaborative filtering based features, you have the logs, if it's the overall listening rate, the popularity. So you have many informations that can be grouped together. So interaction, general context, general information, the tags, is it the genre, the year, and so on. And what you can do is to say that, for instance, well, we are going to predict a skip or non-skip because it's based on the audio signals. So, for instance, I don't know, the transition didn't match, or because the genre didn't match. Or another example of attribution is it would highlight strongly on the interaction features. So you would say, okay, he's skipping everything because he's been skipping everything for the past 10 tracks. So maybe it's in a discovery mode, we say, because it's skipping really quickly. Or make something more complex. For instance, you're just listening to your favorite tracks and not the music you don't know, and so on. So for instance, we have another example in the paper for the movie lens data set 1 million. So what we do is separate between a collaborative based features and content based features, because for movie lens 1 million, we have some content based features, and we try to distinguish when we can make the prediction using only content-based features, so the clusters, so we have access to the tag and year, I think, versus when we have to use the collaborative filtering ones.
Okay, thank you. We have no time for more questions, so thank you, Darius, for your presentation, and we can move to our last speaker, who is Gustavo Penha, and he's presenting a paper entitled "What Does BERT Know About Books, Movies, and Books? Probing BERT for Conversational Recommendation." Gustavo, whenever you're ready, the floor is yours.
Hello, everyone. My name is Gustavo. I'm a PhD student at TU Delft. I'm supervised by Claudia Hauff, and this is our paper on probing BERT for conversational recommendation. So first I'll introduce the task itself of conversational recommendation, and then I will talk about some related work on natural language processing. So here is an example of someone who is seeking information. So he starts by saying that he is looking for a 90s film with great soundtrack. He thought that Power Rangers and Turbo were masterpieces of cinema, and that he's looking for movies from that era with great music. So he wants dramas, thrillers, road movies, adventures. And then someone who is providing information will give suggestions. For instance, you should see Pulp Fiction or Rockstar, and this conversation can go on for several turns. So closely related to this is the field of NLP. And recently, heavily pre-trained language models have shown to be remarkably powerful, and they have been really effective at several NLP tasks. So BERT is one example of those models. Usually the pipeline is like this. The model is trained with lots of GPUs on a lot of natural language data. Then this model is shared, and people can use the weights to fine-tune for the target task that they want to, and this has shown to be really effective, and you can do this with little resources, the fine-tuning procedure. And another related research has shown that those pre-trained models, they are actually able to store some knowledge in the parameters as well. So here's an example. If we want to extract from BERT that where the famous Dutch painter Rembrandt died, we can feed it this sentence to BERT. Rembrandt died in the city of, and we mask the token that we want to predict. And we feed this to BERT, and the output token with highest confidence will be Amsterdam, which is the correct answer here. So we are interested here in using such models, such language models for conversational recommendation. And in this paper, we propose some probes to see what kind of knowledge it's already stored on BERT that could be relevant for this problem of conversational recommendation. So in order to do that, we propose 3 different probes. The first one is the general probe. And basically here we are trying to test if BERT is able to match the item titles with their respective genres. So here we want to see test, for instance, if BERT is able to match Pulp Fiction with drama and thriller. And this could help a conversational recommender to match this request with the correct answer from the pool of responses. Then we propose the search probe. And here we are interested in seeing if BERT is able to match the title with the content of this item. So for instance, we use data from reviews. And then if there's a lot of reviews that mention, for instance, that Pulp Fiction has great music and good songs and so on, it would help a conversational recommender to match this request with the correct answer as well. And last, we have the recommendation probe. And here we are testing if there's some knowledge stored about the sequential nature of the ratings or the interactions. So if we have a data set telling us which movies are frequently watched together, for instance, we use Movie Lens, we could see that Pulp Fiction is often seen after Power Rangers and Turbo, and this could help again in this match. So in order to actually extract the knowledge from BERT, we need to make sentences because that's what the input for BERT is. So here is what we do for the general probe. We just follow previous research on the topic. We make templates as follow. We put the title of the item. For instance, this book is called The Wind-Up Chronicle. And then we say it's a book of the genre, and then we mask the token that we want to guess. And the correct answer, because we have some data sets telling us that, are those tokens. We do the same for the other domains of movie and music albums. And we feed those sentences to BERT. And the second way we do the sentences for search and recommendation is a little bit different, because here we are not the output is not tokens, but here we want to match the similarity between two different sentences. So in the search probe, we match the title of the item with the review, and this is a relevant pair. And we want BERT to rank this sentence before a non-relevant pair that we simply get a random item and we match with the same review. For the recommendation probe, the relevant sentence is based on items that are frequently watched together or frequently consumed together. And the non-relevant pair, we just randomly select the second item. So after we do that, in order to actually extract this knowledge from the language model, in our paper we use the pre-training head. So we use the next sentence prediction head, the mass language modeling head, and also the representation from the CLS token. And we have more details on that on the paper, on how we actually use those BERT components to extract the knowledge. But I'm going to move on to our research questions. So the first one is how much knowledge does BERT have stored about the items, the recommendation items that we are focused here on this paper? And the second one is how can we actually infuse some knowledge into BERT so that it can do conversational recommendation better? So our main findings for the first research question, we first test the general probe. So if we simply remove the title from the template and we put an it instead of the actual title, and we actually say the domain that we are looking for. So here it is a book of the genre and we mask the token. We'll have a prior distribution of the language model for this domain. So we see that it already has some effectiveness when we do that. We actually retrieve the correct tokens. However, when we actually put the title here and replace this with the title, we see that the effectiveness is improved. So we have evidence that BERT does indeed have some information about the genres of the items storing the parameters already. If we look into the search and recommendation probes, we see that BERT has more content knowledge, which is the search probe. It's more effective on the search probe rather than the recommendation one. And this is kind of expected since BERT is a language model. We discussed this a little bit more in detail in the paper. And for the other research question, we have a different setup here. So now we are actually going to train BERT for a task that is related to conversational recommendation. And the task is this. We have the conversational context here on the left. And basically is the context of the conversation so far. So here I have an example where the user says, hi, the other says, hi, what type of movie would you like to see? then the seeker says that he's looking for something like Star Wars, but not Star Trek. And then the correct response that actually happened in this conversation that is a human-to-human conversation is this. Have you seen Avatar? And then we sample some negative candidates, like with BM25 using this as query. So this is an example of a negative candidate. So we train BERT to distinguish between correct responses and negative sampled ones. And if we do that, we see that BERT is extremely effective for this task of distinguish correct responses, ranking the correct responses before the non-correct ones, the negative ones. But if we make this task a little bit more difficult and we make some adversarial candidates, so for instance, if we replace avatar here with a randomly selected item, which makes this an irrelevant response, right? Because we're just recommending random items. We see that BERT has, there's a huge drop in the effectiveness. BERT is not able to distinguish between those anymore, and it's easily fooled by these adversarial examples. So as future work, we think we should look into different ways to combine collaborative filtering knowledge with language models to improve the things that we said that language models are lacking here. We could also probe language models for explainability. So why am I receiving this recommendation? We could ask this somehow for the language model, and also probing other language models for other domains rather than books, movies, and music as well. So that's it. Thank you for your time. I'll be glad to answer any questions.
Thank you, Gustavo, for your presentation. So I encourage the audience to post their questions in the Q&A section of Huang. I will start with one question, then we see some more come from the audience. You observed that basically BERT is affected by adversarial data, and I was wondering if you run any experiments to see like to what extent it's like if there's little adversarial data, or it's like to what extent the model is actually affected by adversarial data.
By adversarial data? Yes.
Adversarial examples, yes, as you mentioned in the paper.
Yeah, so we made some experiments and we saw that actually it's really affected by those. So we tried to do something to improve this. We tried to see if we actually trained the model for the recommendation probe. So we actually show which titles are related. We feed this to BERT. We actually train for the probes that we proposed for recommendation. And we could improve this effectiveness a little bit, but it's still not even close to being really effective. So there's still a lot to do in terms of the collaborative filtering power for those language models, I think.
Okay, thank you. Then we have one question from the audience, which is asking, how do you know BERT does not directly copy from its training data for the closed tests, as BERT is trained on Wikipedia and other internet texts? Is it a honest test then? Okay,
so it could be simply memorizing the categories, which is actually fine. I don't think there's a problem in that BERT is simply memorizing the genres of the items, for instance. But the data that we use is different from the data that BERT was trained. So there's no kind of leakage, let's say, from the train that was the pre-training procedure of BERT to our data. So yeah.
Okay, then one last question, we do have 1 minute. Have you explored the use of BERT in terms of filling in any missing metadata information for items? Do you see any potential use case based on the results?
Yeah, I haven't explored for that, but it could actually be a good idea. However, uh, BERT it would be really unreliable, right? If you have a knowledge base that we can use and export that instead to fill the missing metadata, it's more reliable than just using BERT because it's far from perfect. So we end up with a lot of wrong metadata that you're filling. But yeah, if this is really if the language models really improve on that sense, they could be used for that for sure in the future.
Okay, thank you. So with this, we are ending our session. Let's thank our speakers again. I would like to thank my co-chair Lee, the students volunteer and the technical support, and you all for joining us in this session. I would like to remind you to check out our social activities over the next hour before the next session starts, and I'll see you around. Thank you. Bye-bye.